Okay, so on derivatives, we have a couple rules now. We have sum and difference rules. So when we have functions that are added or subtracted, we could take the sum, the derivative of individual terms, and then add results. We have a product rule now. Okay, we have a power rule. We have a quotient rule. Right, so we got these rules for different types of functions, whether they're added, subtracted, raised to a power, um, multiplied, or divided. Okay. Now there's another rule. It's called the chain rule. Okay, and this is a very powerful rule here for us to find derivatives of certain types of functions. So if we look here, a couple examples here, this chain rule. Well, if we look at this first one, f of x equals 2x plus 5 to the second. We could do this one without the chain rule. Okay, so you have a couple options. One option for this one would be to just multiply it out. Right, if we multiply this out, we would get 4x squared plus 20x plus 25. Okay, I can multiply that out, in which case then f prime of x, all right, would be 8x plus 20. All right, we use our power rules and some other rules implicitly that we aren't really thinking about. We just kind of go through the motion. Now it's pretty easy to take the derivative of 4x squared, the derivative of 20x, and the derivative of 25 and add the results. So we could do it that way without the chain rule. This one, we could do this one. If I multiplied this out, okay, it would look like this. It'd be 2x quantity cubed plus 3 times 2x quantity squared times 5 plus 3 times 2x times 5 squared plus 125, 5, right? And then I could simplify this, 8x cubed. I could multiply this out, and I'd be able to find the derivative. Okay, I could do it. This one, I could multiply all this out, get some big mess there. I could find the derivative then using power rule. Wouldn't want to, okay, but I could do it. But then when we get down to this one here, okay, now this is one where we don't have a rule to do this one. Okay, I could write this as, x squared plus 5 to the 1/2, right? There's an element of rewriting that we still can do. But I can't use a power rule because this is not x to a power. This is this function x squared plus 5 to the power of 1/2. Okay, so this is where this chain rule comes in. Okay, it's going to be useful when there's functions that, well, we could take the derivative using just power rule and some of those other rules. Okay, I could even write this as a product, 2x plus 5 times 2x plus 5, and use a product rule repeated. Okay, but then certain types of functions here, all right, the chain rule is this necessary rule, right? And it really is dealing with composite functions, right? F of g of x stuff. Okay, so let's look over here to kind of formally define what the chain rule is. Okay, so here's the chain rule. Okay, and at any point, you clearly pause it, write down the chain rule. Okay, and then hit play again when you're ready to go. But that we have that if we have some function y being f of u, where it's a differentiable function of u. So in other words, that would mean that y prime is defined for all u. And u, which is my inside function, all right, u equals g of x is a differentiable function of x, right? Well, then that would mean y equals f of g of x is a differentiable function of x. Okay, you can see that composite function there, f of g of x. And then here's kind of the chain rule, okay? And this, we're going to use two different notation. We're going to use our Leibniz notation, so that dy, so the rate of change of y with respect to x, okay? So how is y changing as x varies and changes, is going to be equal to the rate of change of y with respect to u, right? So dy du, and then times the derivative of u with respect to x, okay? And initially that's going to be confusing, okay? And you can see what's nice about this Leibniz notation, use these differentials, dy, du, okay, is that they act as though they're fractions. And if I multiplied these fractions together, and if you manipulate this as though they were fractions, you could see that kind of the du's would cancel and you'd have dy dx equals dy dx. But if we think of what's happening here, right, the inside function, g of x, right, which is f of u, when u changes, right, u changing, right, du is a change in u. When u changes, that's going to cause y to change, right? Right. And in turn, since that's inside here, right, when this inside part changes, that's going to cause the outside function to change as well. Right. So there's one kind of version of chain rule using this Leibniz notation. And then also we can write it like this. So there's another way, that d dx. So I'm going to write the derivative of x, right? Remember, this is to take the derivative of f of g of x, okay? That this is going to be equal to f prime of g of x times g prime of x, okay? So there's the other one, right? That the derivative of f of g of x, so think composite function, inner and outer functions, okay, is f prime of g of x times g prime of x, right? So we have that. Okay, so we can think of the chain rule that way. And yet maybe one more way is if we go with, let's move this right here. We have, if y is equal to f of u, right, where u again is that differentiable function of x, so u is some function of x, whatever it may be, that y prime, let's go here. So this implies that y prime is equal to f prime of u times u prime. Okay, so that's another way we can look at the chain rule here. So kind of three different ways, right? And then to put that in words, okay, that the chain rule is, notice here, I think this is a good place to look. We have the derivative of f, which is our outermost function, right? Here we have an inner function g of x, and we have an outer function f, right? So we have the derivative of my outer function, then evaluate at my inner function unchanged, then times, this is then the derivative of the inner function. So if we put that in words, the derivative of the outer function evaluated at the inner function, then times the derivative of the inner function. All right, and that's a good way to think about how to apply the chain rule. Okay. Jumping over here, we get to then applying what's called the general power rule, which takes advantage of the chain rule. So here we have some function y equals u of x. So some function u of x is raised to the nth power, right? And u of x is some differentiable function of x, all right? And then there's some rational number, okay? So the general power rule is going to be d dx of, all right, so this means take the derivative of this function. And here we have this composite function. We have an inner function u of x, and we have an outer function, this nth power. So if we think the derivative of the outer function, which would be n to the n minus 1, there's the derivative of the outer function, right? So the derivative of the outer function evaluated at the inner function, so that means this is going to stay unchanged right there, and then times the derivative of the inner function, which would be u prime of x, okay? So that is the general power rule, okay? Let me get it, there we go. Nice and, all right, so there's the general power rule, all right? It says we just take the derivative of the outer function, n quantity to the n minus 1, keep that quantity the same, and then times the derivative of that inner function, okay? We're going to be using this one quite a bit. So jumping over here to a couple examples. So here we have y equals the cube root of the quantity x squared minus 1. All right. There's still a lot of times going to be an element of rewriting these. Okay, so now let's rewrite this one first. As x squared minus 1 to the 1/3 power. Okay, x squared minus 1 to the 1/3 power. So now we have an inner function, u of x, raised to the nth power. There's our general power rule. So we take n, so we got 1/3. Everything inside stays the same, right? Raised to the 1/3 minus 1, negative 2/3. Okay, so there's the derivative of the outer function. Now evaluated at the inner function, so x squared minus 1, then times the derivative of x squared minus 1, which is 2x, right? And I'm going to put it in parentheses. I don't have to here, but it's a good habit, because what happens is if this has more than one term and you don't put it in parentheses, it's not correct, okay? It wouldn't be correct. So it's a good habit to just have that in the parentheses. And then, all these we can always rewrite as well. In this case, 2x is in the numerator. The denominator, we have 3, and then x squared minus 1 to the 2/3, right? And then just quickly for this one, this would be 3 over, depending how you write it. You could write it as a cube root of x squared minus 1 quantity squared, like that. Okay, they're all the same. So that's the general power rule for that one, which is really the chain rule, okay, ultimately. So now this one here, all right, what do we have going on here is, well, notice in this one, well, we have a quotient. So we got to do the quotient rule. There's a hierarchy to the rules. The only problem with the hierarchy is it's not consistent. Sometimes it might be the quotient rule first, then the chain rule, then a product rule. Maybe it's a product rule, then a chain rule, then a quotient rule. Okay, so it really depends how it's set up, what you're really doing first. So in this case, we're really doing a quotient rule first. So if I'm going to do quotient rule, I'm going to set it up for myself. I'm going to say, all right, that means this, right? N prime D minus N D prime all over D squared. Okay. And now I could start to fill in. N prime, what's the derivative of x? Well, the derivative of x is 1 times d, so we keep the denominator exactly how it is. So that's the cube root of x squared plus 4 minus n. And now this really comes down to, at any moment, you're really only taking the derivative of one little piece, right? So now I have to take the derivative of this piece right here. That's where I'm at, okay? Ultimately, I'm getting this whole derivative, but I'm really right now just working with this piece. And that's when we're maybe even on this, you go on the side, okay? You go somewhere over here, neatly the denominator, and I think, all right, I got to rewrite this as x squared plus 4 to the 1/3. Now that's what I have to take the derivative of, right? I'm going to run out of room here, so let's give myself a little more room. So we're going to have 1/3. Everything stays the same inside, x squared plus 4 raised to the 1/3 minus 1, negative 2/3. Then times the derivative of x squared plus 4, which is 2x. Okay, so there's the derivative of the denominator. And then in here, just stays the same. Okay, and that is the derivative. That is correct. It's messy. Okay, we could rewrite it, simplify it, do a bunch of stuff. Okay, but for now, we want to make sure we get the rule correct. We have parentheses in the correct place. Okay, so that way we are representing the derivative correctly. Okay, so that's, in this case, we did a quotient rule first, and while we were doing the quotient rule, turns out then we had to do a chain rule. All right, now if we go over here to this one, here you can see a quotient, but the quotient is the inside function, right? 3x minus 1 divided by x squared plus 3 is inside this squared function, this power function. So in this case, the hierarchy is really that we're doing a chain rule first, right? Then followed by quotient rule, okay? So that's really what we're doing first, okay? And there's not one way to do these, all right? I could rewrite this one first by squaring it, and I could rewrite f of x as 3x minus 1 quantity squared over x squared plus 3 quantity squared. Okay, I could do that. Now in this one, you'd really be doing the quotient rule first, and then followed by the chain rule. Okay, so you can see the hierarchy changes depending on, kind of how the function looks. So this one over here, we're going to do the chain rule. So how's that look? Well, it'd be general power rule 2, keep everything inside the same, drop the power by 1. Now what's inside? Well, 3x minus 1 over x squared plus 3 times, now what? Times the derivative of the inside stuff. But that's going to be a chain rule. So we're going to have parentheses, parentheses, minus parentheses, parentheses, over parentheses, squared. There's my template for the quotient rule. In here, the derivative of the numerator. What's the derivative of 3x minus 1? 3 times the denominator, x squared plus 3, minus the numerator times the derivative of the denominator, 2x, and then all over here we just rewrite the denominator, x squared plus 3 squared. All right, so in this case, that's that derivative. What is the derivative of f of x here? Right there it is. And we could multiply stuff, combine like terms, simplify this. It's not really the point right now. That's that's algebra 2 type stuff, algebra 1. Combining like terms, squaring binomials. Okay, so that's nothing new. Okay, so you can see there, that's a quotient rule, all right, within the chain rule when you're doing a power, okay, the general power rule. Let's jump over here, do some trig functions, all right. So we did sine of u, or we did the derivative of sine of x. We did the derivative of cosine of x. Tangent of x, the derivative of that was left as a little exercise at the end of the quotient rule video. So here, generally, if we have sine of u, cosine u, tangent u, and now in this case, u, all right, just keep in mind, u, right, is a function of x. U is a function of x. All right, so what's the derivative of sine of u? The derivative of sine of u is going to be cosine of u, and then times u prime. Because we have the outer function is really sine function. So the derivative of the sine function is cosine. Keep the inside function same u, and then times the derivative of the inside function u, which is u prime. Over here, the derivative of cosine of u is going to be negative sine of u times u prime. And tangent of u is going to be, right, secant squared of u times u prime. Okay, so that's those trig function derivatives. Okay, so there's our trig functions, more generalized here. So going over here, a couple examples. So if y equals sine of 2x, right? Y equals sine of 2x. What is the derivative of sine of, in this case, here's our u, right? The derivative of sine of 2x is going to be the derivative of sine, which is cosine of 2x, then times the derivative of 2x, which is 2, okay? And then generally we would write that as 2 cosine of 2x, okay? So there's that one. Right. If we go over here, what is the derivative of cosine of 4x squared? Okay, you gotta be a little careful here, right? Yeah, before we go ahead and do this one, notice it's not 4x squared, it's 4x squared, okay? So this, we would first, most likely, it's not, you don't have to, we're gonna do this one a second time and do it a different way, is that I would want to multiply 4x out to make this cosine of then 16x squared, okay? Because now, okay, let's slide this over now. So here, what's the derivative of cosine of u 16x squared? It's going to be negative. Now, once you get used to this and you know what you're going to have a little ahead of time, I'm going to leave a little space, negative sine of 16x squared, then times the derivative of 16x squared, which is 32x. Okay, so negative 32x sine of x squared. Okay. So there's the chain rule there for that trig one. Now, another way to do this one, okay, would be to, right, we're going to really see this in the next little segment here, is y prime is equal to what? Well, the derivative of cosine, which is negative sine of all that stuff, 4x quantity squared. So like I said, you're only ever taking the derivative of one little piece at a time. I only got to worry about this. My problem initially is taking the derivative of the outer function cosine, which is negative sine. Then I pay my attention to the next little piece. Now, at this point, I have to take the derivative of this right here. So that's as if that was your new problem, that if you started with that, okay? Well, if I started with this, I might look at this and go, oh, that's a general power rule, which would be the derivative of what? Times outer function derivative of 2. Inner function stays the same to the first. What's this here? Well, this is 4x, okay? And then times the derivative of 4x, which is 4, okay? And you can see here that you clearly get the same thing. 8 times 4 is 32. I get negative 32x, okay? So that's a different way you can go about doing that one, all right? And you just build up an intuition. What's a quicker way? Sometimes it might be to multiply that out quickly, do it that way, or that you want to just leave that as is, okay? And then we could simplify that right a little neater, okay? So there's a couple trig, okay? Now we're going to bump it up a notch here. So repeated use of the chain rule. So kind of like the product rule when you have, f times g, that extends to f times g times h times, any amount of functions multiplied together. The chain rule is the same thing. Here I have an inner function, an outer function, another outer function, okay? It's almost like you can follow a pattern, just like the product rule when we did the f times g times h, and that kind of prime notation derivative just bounces down the line. Similar here. And what helps is if you think about, in words, how to do a chain rule. It's the derivative of the outer function evaluated at the inner function times the derivative of the inner function. So initially, the derivative of the outer function, and I don't know what function f is. Maybe it's a square root. Maybe it's something to a third power. It's a power function to the third power. But whatever function f is, I can represent the derivative of f by just writing f prime. So the derivative of the outer function, right there, f prime, evaluated at the inner function. So now evaluate at g of h of x times now the derivative of this inner function. So now this is my new problem. I forget about everything else I've done. And you imagine that this is the only problem that's staring at you. I have to find the derivative of g of h of x. Well, that's another inner outer function. So what do? Take the derivative of the outer function, which is g prime, evaluated at the inner function, h of x, times the derivative of the inner function here, h of x. Okay? And then we're done. And at one point, well, we have the derivative of x, but the derivative of x is just 1. We don't write that. Okay? So there's, a repeated, all right, f of g of h of x. And you can see how the prime kind of just bounces down the line from f to g to h, okay? The derivative of the outer function, keep the inside function the same, times, well, look in here now, the derivative of the outer function, keep the inside function the same. Then look here, the derivative of the inside function, right there, keep the inside function the same. Next. All right, so let's do, I got 3 of these here we're going to do, all right? So you kind of using this idea. So here I have sine cubed of 4t, all right? Now this one is one that, a lot of times when you look at this way, right, you get a wrong answer. So realize what this means. Sine cubed of 4t means what? It means I have sine of 4t raised to the third power. Right? That's what sine cubed of 4t means. It means I have sine of 4t raised to the third power. Now when you look at that, I have what? I have an outer function. The most outer function I have is this cubic function. Then I have an inner function. But even this has an outer sine and inner function 4t. So to take the derivative of this, I have to take the derivative of the outermost function, which is that cubic function. So I'd have 3, keep everything inside the same, raised to the second power. Now I have to focus on what's inside here. Well, sine of 4t. Now what's this derivative? Well, here I have an outer function, inner function. So I multiply by the derivative of sine, which is cosine, of inner function stays the same. And now lastly, I have to multiply by the derivative of the inner function 4t, which is times 4. Okay? And then we could tidy that up and write it something like what? 12, all right, times cosine of 4t times sine squared of 4t. Okay. And that's kind of the thing that you would see on, if you're taking the AP test, that's the answer you're going to see on multiple choice. Okay. So there's a repeated use of the chain rule. Okay. Now these sometimes get a little tricky when we start to take away, what's familiar, sine, 4t, linear functions, cubic functions, and we write it just in general, f and g and x. Don't overcomplicate it. We have an outermost function and we have inner functions, right? So what's the derivative of f of g of x squared? You just say the derivative of the outer function. I'm going to, grain it and beat it into your heads here. The derivative of the outer function, f prime. Keep the inside function the same. Times. Now work here, g of x squared. The derivative of g of x squared is the derivative of the outer function, g prime. Keep the inside function the same. Times now the derivative of the inner function, 2x. And now you're done. Okay. So for y equals f of g of x squared, y prime would be f prime of g of x squared times g prime of x squared times 2x. Okay. Just takes a little practice, a little attention to detail. And then one more here. We have the square root of f of sine of x. All right. And something we would probably want to do here is to first write this as f of sine of x raised to the 1/2 power. And now to find this derivative, I'm going to have 1/2, keep everything the same, raised to the negative 1/2, 1/2 minus 1. There's the power rule, right? So that's my outermost function, the 1/2 power. So I take that derivative, now I keep the inside the same, so just rewrite it, f of sine of x. Now I got to take this derivative. What's the derivative of f of sine of x? Another outer inner function. So times the derivative of f, outer function derivative, evaluated at the inner function, keep the same. Now times the derivative of the inner function sine. Now be careful here, don't write this down. Okay, that's not right. This says f prime of sine of x minus cosine of x, but we need it to be times negative cosine of x. So make sure it's in parentheses. Okay. The other option, at some point is to put the negative in front. Okay. But that would be this derivative. Okay. We could simplify, get rid of the negative exponent, but it's more about the process of understanding how to take a derivative of, a function that looks like that. Okay. Using the chain rule. So that's the introduction there to the chain rule. A bunch of examples, different scenarios you run into, and you really got to become comfortable with doing this and quite honestly, doing it quickly. Okay. Initially, it might not be that way, but through practice and repetition, you get fluid with doing these. Okay, and you could just see it and what to do. You got to pay attention to detail. Make sure you're using parentheses in the correct places. And thinking about the stuff that I was explaining here in this little video. At any point, pause, rewind, watch it again to understand it. Okay, don't just listen and hear and write. Okay, make sure you're understanding what's being described. And when you have this feeling that you fully get and understand in your heads, in your minds, what's going on here, then you can proceed and move on. Okay, so watch this over. Reach out. Let me know if you have any questions. Going to be a lot more to come here with the different applications of the chain rule and all the derivatives and stuff, and still a lot of work to do. All right, so keep it up. Been doing a good job.